This lecture video is, it's called Magnetic Field of a Current. But what I'm going to do in this video is I'm going to talk a little bit about interactions. In particular, we'll talk about the gravitational interaction, the electrical interaction, and then I'm going to, by analogy, talk about magnetic interaction. Right? So at first, right, I'm hoping that what I say about the gravitational and electrical interactions doesn't surprise anybody. And then you're going to get a theme or a pattern, and I'm hoping that what you walk away with is thinking about the magnetic interaction in a particular sort of way. So let's start with a gravitational interaction. Gravitational interaction happens, let's say, between mass 1 and mass 2, right? It's an interaction between masses. It's fundamental and you can't turn it off. So whenever you talk about an interaction, and this actually might go all the way back to Newton, and it's in particular I'm talking in terms of Newton's third law. Whenever you talk about the gravitational interaction, right, you talk about the gravitational interaction. That's the interaction we're talking about. And then in this gravitational interaction, there's actually just two forces. And by Newton's third law, these two forces are equal and opposite. And so they come with labels, right? So there's a force that acts upon M1. You might say it's the force on M1 by M2 due to gravity. So there is a force on M1 by M2, right? So it's an interaction between these two objects. And the reason is gravity. We say via gravitational interaction. So there is this force. I just drew it. It's the force. Can you see that the arrow, the force arrow, is attached to M1? It's pulling on M1 towards the right, which is towards M2. There's also a force on M2 by M1 instead. You can see that I switched the labels. And this is also via gravity. It's via the same interaction, the single gravitational interaction between these two masses, right? So that arrow is attached to M2, points towards M1 because gravity is attractive. And when you look at these two forces in the same coordinate system, right, you can see that they point in opposite directions, but they're going to have the same strength. So we put an equal sign, but with a relative minus, right? That's Newton's third law. Okay, so interesting thing is electrical interaction. So let me put electrical. Actually, let me back up. I wanted to go a little bit further with the gravitational interaction. All right, so mass interacts with mass, right? And we have a field concept, right? So there is the gravitational field that is because of M2. And if you multiply by M1, this is the force on M1 by M2 via gravity. Right? So there is a gravitational field surrounding M2. So, right? So surrounding M2, actually, let me take that back. Let me do it in this sort of vague, right? So M2, take the opacity down. So M2 spreads its gravitational field out in space, right? This is M2's gravitational field. And can you see that M1 sits in it, right? So M1 sits in M2's gravitational field. So this is the gravitational field of M2. But there's a parallel kind of like way of saying stuff from the point of view of thinking about the gravitational field of M1. And if you multiply M2 times that field, you get the force on M2 by M1, right? Via gravity. And let's say that the gravitational field of M1, I'm going to indicate with a different color, indicate it with red, right? And we would say that M1 has a gravitational field that extends out into space, and M2 sits in it. So M2 feels a force because of M1's gravitational field. And this is the sense in which there is a field concept, right? So, okay, so no big deal. Gravity is an interaction based on mass. So let me say it this way. So objects with mass have gravitational field That's one thing, right? All you got to do is have mass. If you have mass, then you're going to have a gravitational field. And also participate in gravitational interactions, right? And all you need in order to be able to participate in gravity is you have mass. And all you need to have a gravitational field is you have to have mass, right? So that this is a field concept for gravity. Electrical interactions are really similar. Right? So let me do this kind of quickly. So let's say we have a charge called QA. It's either a positive or a negative charge, right? And surrounding QA is its electric field. So this is the electric field of QA. It extends out in space and is weaker further away, just like gravity. And if there is another charge, QB sits in QA's field. So this field out here, let me increase the opacity. This is the electric field that belongs to charge A, right? And the way that we understand the force on charge B is we take the charge A and multiply by the field, the force on QB, excuse me. So this is acting on QB, and actually it's charge A's electric field. I'm sorry, I stumbled there. But can you see how similar this is to the gravity, right? So instead of an electric field, I have a gravitational field. The gravitational field belongs to a certain mass, and a different mass feels it. So here's the force on the other mass, right? This is how mass 1 feels the field of mass 2. And likewise, it's the same kind of idea, field concept for electric force. So again, to participate in electric interaction, you must have charge, right? So the thing, right? So we have some object called A. If the object A does not have charge, it cannot have an electric field, and it cannot participate with electric force, right? That's why they say neutrons, which are neutrally charged, right? Because they have no charge, they do not have field, and also other electric fields can't affect them. But neutrons do have mass, so neutrons can participate in gravitational interaction. But to participate in an electrical interaction, you must have charge, right? And you must have electric field, right? Actually, let me put it in the way I put gravity. So objects with mass they're going to come with gravitational field, and objects with mass will participate in gravitational interactions. That is, they will feel the field of other masses, right? So let's put it that way for electricity too. So objects with charge, right? So sorry, I'm turning this around. They will participate in electric interactions, and they will have an electric field. So let's change that. Okay, so objects with charge. Now, what about magnetism? Right? So mass is the source of gravitational field. Charge is the source of electric field. What is the source of magnetic field? Right? So to answer this question, you just have to ask, what participates in magnetic interaction? Right? What kind of thing participates and has magnetic force? And one answer are these things called permanent magnets, right? I've been drawing them to look like, there's a north and a south. Sometimes I've been drawing horseshoe magnets. They still have north-south poles, right? And these things have magnetic field, right? Field lines come out of north and go into south. So it emerges from the north and goes back into the south. Does it on both sides, right? And further away is weaker, right? Same over here. Goes from north to south, right? I'm drawing the magnetic field, right? And there's really weak field lines far away, right? Just like what you expect. So permanent magnets participate in magnetic interactions. That's really easy because, if you take two north-south magnets and you put them nearby each other, if you put them this way, they repel. But if you put them like this way, they attract, right? So here is all you need to know there is interaction, right? So magnets interact with magnets. But you've also heard here is a little bit more physics. Currents. So current carrying wires, right? Currents and moving electric charge also participate in magnetic interaction, right? So for example, we have these sort of two equations. We have the force on some charge Q, right? This is the magnetic force law. So you have a charge Q with velocity V. If it's moving through a background magnetic field, this is the magnetic force on the charge Q. What this means, though, moving charge is a magnet. So a moving charge is a magnet. We also have this other force law. The force on a segment of wire, it's equal to I L cross B. So the source of the magnetic field could be one of these bar magnets or this horseshoe magnet, right? So you have a moving electric charge will interact with that magnet. But then I say, well, if it participates in magnetic interaction, then that means that a moving charge is itself a magnet. Likewise here, if a current carrying wire feels a force by some magnetic field, that means a current carrying wire is a magnet. What's interesting is actually up here, a moving charge is a magnet. So that means that a moving charge is going to have a magnetic field, right? This is the magnetic field due to a charge with some velocity. But also what's really interesting is a moving charge also has electric field. So a moving charge actually is an interesting thing because it's going to have with it, if you have a moving charge moving through some space, then surrounding that charge is both electric field and magnetic field. But a current carrying wire, even though you might have a current running down this wire, there is no net charge anywhere. So what this means, right, is everywhere you look and you find a proton, you find an electron. It's just that the electron happens to be flowing down the wire. But what I mean is anywhere you look, in any place on the wire, like say inside of this little square, you will always find the same number of pluses as minuses. It's just that the minuses are moving, right? So that means there's no net charge, which means that you're not going to have, excuse me, I meant it the other way. You're not going to have any electric field, or at least the value of the field is going to be 0, but you are going to have magnetic field. So the magnetic field is surrounding the wire is not going to be 0 because compasses or magnets are going to feel a force and a twist. They're going to feel a torque and a force. So a magnet near a current carrying wire is going to accelerate, And that's pretty cool. Yeah, so a current carrying wire is a magnet. So now what I'm going to do in the next video is describe how is the magnetic field related to the current and distance from a wire. And the name of the law, it's named after two people whose names are French. It's Biot and Savart. It's the Biot-Savart law, right? So that's what I'm going to tell you about in the next video. It's the way to get the magnetic field from current.